And the first one that I want to introduce to you is probably as different from X-rays as night is from day. So I'm going to illustrate that difference by showing you the difference between night and day. So here's the Earth, and over here we've got daytime, obviously over here we've got nighttime. Now, during daytime we see the Earth as we expect to see it on a map. We see pretty much what's there. That's like shining X-rays through our body. We see what's there. But at night time, well, we switch the light off. We expect to see nothing at all. But actually, we see evidence of civilization on the Earth. The Earth emits its own light. What about if we could make our bodies emit their own X-rays? If we could do that, we might not get a picture of so much what's there, but what our bodies are doing. Well, it is possible to make our bodies emit X-rays, and the story of how we do that begins at about the same time that Roentgen discovers X-rays with this chap, Henri Becquerel. He was playing around with photographic film at about the same time that Roentgen was discovering X-rays. And he made the mistake of leaving some film in a drawer with a lump of rock, and he noticed that the film got fogged. He made a note of that, but he left all the details up to this feisty young lady from Poland. Her name, Marie Curie. She'd come to France at a time when women really weren't supposed to study at university at all. She blagged away into Becquerel's lab, and there she met and married Pierre Curie. And together they worked on this problem of the radiation from the rock. They called it radioactivity, and Marie Curie went on to win the Nobel Prize for isolating the element radium. Radium caused a stir just like X-rays had caused a stir. Everybody wanted a piece of the action. Everybody wanted to have radium on their brand. Everybody went bananas about radium, and it wasn't always for the right reasons. Radioactivity burst onto the scene, but it didn't find immediate use in medicine at all. And the reason? Because nobody really knew how it worked. Science at that point didn't really believe that atoms were real. And the first milestone is made by this guy, Ernest Rutherford, and he discovers that the atom has got a tiny, really very small nucleus at its centre. And that nucleus is composed of protons and neutrons. And if you get the balance of protons and neutrons wrong, that's what makes things radioactive. So if we want to unbalance the nucleus at the centre of an atom, we need to shove in an extra proton or two. But that's tough. If you were to grab hold of a proton and stick it on the bottom of your shoe and try and push it into a nucleus, and we're just talking about one proton and any nucleus you happen to find lying around, you wouldn't be able to do it because the force of repulsion is too big. It would suspend you in midair. Of course, you can't do that. So we're going to have to wait a little bit longer before science finds a way to put a proton into a particle accelerator and give it enough oomph to get inside a nucleus. And that doesn't happen until the 1930s, when these two guys come along and build the first particle accelerator called a cyclotron, and it's a sort of early form of the Large Hadron Collider. And when this comes onto the scene, suddenly the world is able to make radioactivity for itself. And we're able to say, well, can we put this radioactivity inside people's bodies and see what comes out? Well, we can, but we need to be careful. And the reason we need to be careful is highlighted by this chap, Alexander Litvinenko. He was a KGB spy, you may remember 5 years or so ago, came to this country, and the KGB really didn't like that. So they decided to bump him off. One day he fell ill, a couple of days later he was in hospital, and he was really rather unwell. He died 3 weeks later, and nobody knew what was wrong with him. At autopsy, they found trace amounts of the element that Marie Curie had discovered 100 years before, radium. Just a few nanograms of that had been put into his tea, and it killed him. So we need to be careful if we're going to put radioactivity inside our bodies. Now, some of you will know that radioactivity comes in different flavours. There's radioactivity that emits alpha particles, and they're what did this. We want to avoid that. There's radioactivity that emits particles called beta particles, It's just another name for an electron that comes spat out by the nucleus. And they're pretty dangerous too, so we pretty much want to avoid that for the same reason. There's radioactivity that emits gamma particles, and that's just another name for X-rays that come out of the nucleus. So those are the ones we want. We also want these radioactive materials not to be radioactive for too long. So that lessens the list of elements that we can choose. In fact, the list is really rather small. There are just 7 elements that are worth considering for injecting into the body. There are these 3, krypton, xenon and iodine. 2 of those are gases, so we could breathe those in. Iodine's quite useful. The body uses it to make certain hormones. So they're quite useful. Next on our list, this motley crew. Body's got no use for those whatsoever, but we're running out, so we've got to use some of those. Thallium happens to be, the one at the bottom, happens to be the most poisonous element in the periodic table. 1 gram, that will kill you. So we definitely don't use 1 gram, but we still use it. And last on the list, an element that didn't exist on planet Earth until the 1930s. Technetium turns out to be just about right, just about the perfect element for injecting into our bodies. There are lots of things wrong with it, but this is the element that we tend to choose to put inside the body. And in the 1950s, it was produced fairly cheaply, and also at the same time this guy comes along, an American, and builds a camera that's able to see that radioactivity. So this is called a gamma camera. There are 2 cameras here. Let's strip away one of them, let's focus in on the other one, and right at the heart of this camera is a very simple material. I've got a lump here. It's called sodium iodide. It's just like sodium chloride, the stuff you put on your fish and chips, except the chlorine's been replaced with iodine. So it's a pretty simple material. But the neat thing about this material is that when you shine X-rays on it, it gives off little flashes of light. So if we can see those flashes, we've got a hope of building an image of radioactivity in our bodies. And we do that by bolting some of these things onto the back of our crystal. And these are called photomultiplier tubes, and they're just very, very sensitive light detectors. But there's a bit of a problem. These things are huge. They're also quite expensive. If we were to build a picture by bolting an array of these on the back of a whopping great big crystal, then it might look something like this. So these are our light detectors. If we took a picture of somebody's face, it might look like that. We wouldn't be able to see any useful detail. Actually, we probably need to make these a bit smaller to see a bit more detail. These cost about 100 quid each, and they don't get any cheaper as you make them smaller. So that picture's costing us about, well, 64 of these, £6,500. If we double the number in each direction, suddenly we're spending £25,000 to get that picture, now 100,000, and so on. And before we've got a picture that we're really happy with, we've spent 25 million quid. So that's quite an expensive camera. We actually need to be a little bit more ingenious. We need to stick with detectors like this and hopefully end up with a picture like that. And to explain how we manage that, I've enlisted the help of Savian. Do your business there, and I'll explain what Savian's doing in a moment. And then I've got these 4 gentlemen. You know what you're doing as well. So if you'd like to take to the stage as well. So what we're going to do is recreate for you a light flash. We want you to see the light flash. So instead of particles of light, I'm using these plastic balls. Savian is providing the energy for our flash of light, and these 4 gentlemen are the very large and bulky, but quite sensitive detectors. Savian's putting all the energy in, he's nearly there, and when he's finished, we're just going to launch the flash of light and see how many particles each one of our super sensitive, but quite bulky detectors manages to take on. Thank you very much. A small round of applause for our muscular gentlemen. So, gentlemen, are you ready? 3, 2, 1. So what I want you to do is quickly to count how many particles you detected in your detector, and I'll be asking for the results in just a moment. The gentleman over here, how many? 28, thank you very much. And over here? 25. And here? 7. And here? 20. So what we do is we allow our detectors to take a vote, and the proportion of light that they see determines where we think the light flash must have originated. So we've got these whopping great big detectors, but because they all use this sort of fair voting system, we can position the light flash quite accurately between them. So we've built ourselves a very sensitive light detector, but we're not quite there yet, because we've built ourselves a screen, and a screen by itself is not an imaging device. If I just see if I can illustrate that over here, back to our cross, here's my screen, it's very sensitive to light, but if I take away the lens, I haven't got a picture at all. What I need is some kind of lens that will focus the X-rays or the gamma rays from our patient's body. That's just what we see when we look at our own eyes. We need a lens in front of our retina. Anybody, any suggestions as to what we could use to focus X-rays? I'm not going to pass the microphone round, because if anybody comes up with an answer, please tell me, and we will file a patent on it, because nobody's come up with anything that will focus X-rays. That's not to say it's not impossible. As far as we know, it's physically possible, but nobody's done it. Nobody's managed to do it technically. And there are real difficulties, obviously. So what we need to do is to replace our lens with something else. And what do we use? Well, it's a super high-tech piece of imaging equipment, not unlike this, a big bundle of straws. And if I try and show you how this works by going back to our screen with nothing in particular on it, and I move the source a bit closer so I can sandwich the straws in between, I hope you can see that we do get a picture of that cross. So this is our poor man's lens for X-rays, and that's what we have to use. So let's add that ingredient into our camera, and then we're finished. We've got ourselves a way of seeing X-rays that are coming from radioactivity inside our patient. So we turn this onto our patient, and we see lots of little tiny flashes, each one a radioactive decay inside our patient. And if we build those up over a period of a few minutes, we get a picture something like this. Now, this particular radioactivity was designed to go into the patient's bones. And what it does is it shows us how the patient's bones are growing. So although this looks a bit like an X-ray, it's actually very different. And let me see if I can illustrate how it is different. So we've got 3 of these pictures. 2 of them are about my age, but 1 of them is about the age of these gentlemen over here. Right, who thinks that the teenager is A? Oh, we've got a couple there. B, couple more. C. Well, actually, the B's and C's were fairly good guesses. It isn't A, but it actually isn't C. What's going on, if you look, let's say, at the knees on B, they're very bright here, but not so bright here. And actually, if you look at all the bones in this skeleton, they're all bright at the ends. And that's because these lads are still growing, and their bones grow from the ends. They pump bone into the middle. So that's a teenager in the middle, and that's me on the left. This poor guy has got bits of bone growing all over the place, in his ribs and in his shoulders, that really shouldn't be there. And unfortunately, that's a sign that a cancer, some cancer that's developed somewhere in his body, has spread and gone into his bones. So that's quite a bleak picture, but an important diagnosis. Let me just show you one other way that you can put radioactivity inside the bodies. You can put radioactive junk inside the body, and the body will try to get rid of it, and it uses the kidneys for that. So here we're injecting some radioactive junk. It gets sucked out of the blood by the kidneys, and we can follow it over a period of, say, 20 minutes, and this is a little movie sequence of that. And we can be fairly quantitative about this, so we can calculate some numbers. If I draw around the 2 kidneys, I can count how much radioactivity there is in each of these kidneys over the 20 minutes. And I think you can see that the left kidney sucks this radioactivity out of the blood and then sends it away into the bladder so that it can be gotten rid of when you go to the loo. Whereas the one on the right does exactly the same. It sucks this stuff out of the body, but it has a problem. It's got some kind of blockage, so it can't get rid of this urine so easily. So there's a problem with this right kidney, and that's an important thing to see, because the kidneys can function like this for a long time, but eventually that kidney is going to poison itself.